Hello and welcome to section 15.7 on Stokes' theorem. All right, this is really exciting in part because we're almost finished with the material for the quarter, but also these last two theorems, Stokes' theorem and the divergence theorem, are the crown jewels of everything we're studying this quarter. And so many of the concepts we've seen come together in these last two sections in a really beautiful and unifying way, and so enjoy. All right, so to introduce Stokes' theorem, let's have a look at Green's theorem real quick. Recall Green's theorem says that the total circulation of a vector field F throughout some region R is equal to the circulation of the vector field on the boundary of the region R. And so to fill that out in a little more detail, remember that the quantity del Q del X minus del P del Y, this is by definition the two-dimensional curl of the vector field F, and it's measuring the rotation of the vector field at a point, or put another way, it's measuring the instantaneous circulation of the vector field in a little neighborhood about a point. And so if I sum up all these little instantaneous circulations throughout the region R, that's going to give me the total circulation throughout the region. And Green's theorem says that that total circulation is equal to the circulation of the vector field that's happening out here on the boundary curve. That's what this line integral over this boundary curve C is measuring off here on the left. All right, so now while this is a statement about a two-dimensional vector field F and a region R in the xy plane, we can think about this statement in R3 by just treating R as a flat surface in R3, and it just happens to be lying in the xy plane. And noting that since the surface is flat, okay, the unit normal vector at any point on the surface is just going to be k or negative k. Our choice will depend on the orientation of the boundary curve C. Okay, but the point here is that you can treat this region R as an oriented surface in R3. And the reason why I'm bringing this into the picture is that this really is just a special instance of Stokes' theorem. Okay, Stokes' theorem is just a three-dimensional version of Green's theorem. And so what does it say? Well, it says that if I have a surface S in R3 and its boundary curve, you see here in blue, I call C, Stokes' theorem says that the surface integral of the curl of our vector field F over this surface S is equal to the line integral of our vector field over this boundary curve C. Okay, so a couple comments here. First, recall the circulation form of Green's theorem, which is really just a recopy of this statement, where we just note, right, that this quantity by definition was the two-dimensional curl of the vector field F. Well, Stokes' theorem, here we're integrating the three-dimensional curl now of the three-dimensional vector field F. And as we saw in section 15.5, right, the curl here is measuring the rotation of the vector field F at points along this surface. So this surface integral now on the right is measuring the total circulation of the vector field throughout the surface S. And Stokes' theorem says that total circulation is equal to the circulation of the vector field that's happening down here on the boundary of the surface. Okay, now orientation is going to play a big role in this, and we now have two orientations we're going to have to be mindful of. There's the orientation on the surface, just as we were looking at orientation of surfaces in the last section, but then we also have the orientation of the boundary curve. And we want these two orientations to be compatible. And what do I mean by that? Well, we're going to use the right-hand rule to uh, uh, give us the convention for compatibility of orientations. And so I want to say more about that because, again, this is an important issue when applying Stokes' theorem. So what the right-hand rule says, it says that if the fingers of your right hand curl in the positive direction around your boundary curve C, then your right thumb will point in the general direction of the normal vectors to the surface S. Okay, so if this is the case, then we say that the orientations of the surface and the boundary curve C are compatible. So let's say I orient the boundary curve C in a counterclockwise fashion if I'm looking down on the curve. So what this convention would say then is that if I curl my, and please forgive me this really horrible drawing of a right hand, but I think it conveys the idea that if I curl my right fingers in the direction of positive orientation for C, right, which again is counterclockwise in this case, then my right thumb is going to point in the general direction of the normal vectors to the surface. And keep in mind, right, the general part of that, right? At every point on the surface, there's really two choices for normal direction, right? I could choose the outward normal or the inward normal. And so if these two orientations are going to be compatible, then, right, given the direction of my right thumb in this case, right, I'm going to use the outward normals. Okay, so what if uh, this is my surface and I give the boundary curve a clockwise orientation when looking down on it? Well, now, right, if I curl my right fingers along the positive direction for C, I'm essentially going to have to be turning my thumb upside down to follow that. And now I'm going to be choosing the inward pointing normals. Okay. So in this case, these orientations would be compatible. Okay. So Stokes' theorem here, again, which is making this statement about these two types of integrals, right? The surface integral of of the curl of our vector field and the line integral of our vector field around the boundary curve assumes that the orientations of the surface and its boundary are consistent, or in other words, compatible, meaning they follow this right-hand rule convention. Okay, so what if that were not the case? Like, let's say, I had a clockwise orientation for the boundary curve, but then the unit normals were pointing outward. Well, then Stokes' theorem would just say these corresponding integrals would be equal but opposite, right? You pick up a negative sign. Okay, cool. So now, last thing I want to say here in this video, just a few comments about the intuition for why Stokes' theorem is true. And it's really just the same intuition that we used in arguing why Green's theorem is true. So let's say I have a little patch of surface, and I break this up into these four little sub patches. And I'm looking at the rotation of my vector field, right? Or in other words, the instantaneous circulation of the vector field in a little neighborhood. Okay, so you want to think about each one of these little subregions as being infinitely small. Think about them on the differential level. And so if I were to measure the circulation around the boundary of this portion, okay, well, I'm going to be moving counterclockwise, supposing that my field is rotating counterclockwise. But then if I look down, say, at this region, right, notice along this common boundary piece right here, I'm going to get equal but opposite contributions for circulation. And so I'm going to get cancellation along this common boundary piece. And likewise, I'm going to get cancellation here from these two regions, cancellation here from these two regions, and cancellation here. Okay, so in total, what I can say is that the total circulation throughout this patch is equal to the circulation on the boundary of the patch here in blue. Okay, so then if I have a surface like this and I'm looking at how the vector field, right, is circulating throughout points on the surface, then just by applying this argument, right, to these little small patches, think about, taking like these four right here. This argument right here would say that, right, the net circulation of these four little sub patches, they're gonna give me the total circulation just on the boundary here. But then just go to these patches, right? In other words, continue to let this grow. Okay, you're gonna get all this internal cancellation, and what you'll get in net is the circulation out here on the boundary, right? That's the stuff that's not going to cancel out. And that's really just what Stokes' theorem says. It says circulation throughout the surface S is equal to the circulation on the boundary, and that's because of all this internal cancellation. All right, cool. Well, that's a good place to stop as an intro. And in the next number of videos, we're going to go ahead and illustrate Stokes' theorem with some calculations. So I will see you there. Thanks so much.